arch by 5 degrees a day until it was in position.
It's still grip, move, grip.
That's correct,
move,
yes.
grip, move, grip, move. It's
Yes.
the same process. It's a giant pressing mill.
Exactly.
Now, these things are capable of lifting, what, anything?
I would say anything.
The jacks that pulled the Wembley arch up didn't just have one strand, they had 38 each. The combined pulling force of all these jacks was nearly 12,000 tons. That's the equivalent of 6,000 4x4s all pulling at once. This massive feat of engineering was only possible because of a principle previously used in a climbing knot. But getting it up there was only half the story. There was still the roof to consider.
And that was the next big challenge. Just how do you connect a massive arch to an even bigger roof? For the answer, the engineers had to reach for the sky.
The architects at Wembley Stadium wanted the mighty arch to hold up as much of the 11 acres of roof as possible. If the engineers didn't get it right, the whole thing would collapse into the stadium below.
Not only did 7,000 tons of roof need supporting, the engineers needed to find a way to secure 1,750 tons of the arch itself, freestanding high above London.
Engineers needed the arch to hold up the roof, but then they had to stop the arch from buckling under the weight. So they turned to the first aviators for inspiration. Though the Wright brothers famously took their first powered aircraft into the skies over America in 1903, Wembley's connection with aviation goes back even further, nearly 100 years earlier, to an English inventor, Sir George Cayley, who was already testing model gliders. Cayley's pioneering designs, like this modern replica, would influence all future flying machines. And his glider would help the Wembley arch hold up the roof.
Cayley was the first to really grasp aerodynamic techniques. He was confident he could get someone into the air safely. It was just getting them back to Earth safely that was the tricky bit. He realised that if he wanted someone to fly his glider, they needed to be able to land it safely, and to do that, he'd need strong, rolling undercarriage, and that's where the problems set in.
All Cayley had to work with were wheels made of wood. So to find out just what Cayley was up against, I've enlisted the help of James Bond stuntman Derek Lee and his bike.
What we have here is an experiment to try and demonstrate the problem facing Cayley. So we have a bicycle, but we've replaced the front wheel with one made of wood. Well, the point is that the problems with wooden wheels for Cayley for his glider were, first of all, that they were heavy. So to try and fly them, it's really, really heavy. I can feel that straight away, which is going to affect your flight. What I had said there and what I did say is flight. Because what we're standing on is the last piece of kit. This is a ramp. You're going to try and actually jump this bicycle.
I'm going to jump it. Not very far, but I'm going to try and jump it.
Oh!
The wooden wheel shattered on impact. It just wasn't strong enough. Not great for a glider coming back to Earth.
That's where Cayley's other great invention came in. The wheel. Well, not the actual wheel, obviously, but in 1808 he introduced a revolutionary new type of wheel. It might look like just a bicycle wheel, but that's because Cayley's invention became the bicycle wheel as we know it today. Cayley's new idea revolutionized thinking at the time. Instead of using spokes under compression, he put his spokes under tension.
Equally tensioned spokes constantly pull the wheel together and give it strength. On impact, all the spokes act together to keep it in shape. And materials that are good at withstanding tension can also be light, like wire. So these new wheels were much easier to get off the ground and much less likely to break on impact, essential for landing gliders safely. Fast forward 2 centuries. BMX riders now rely on Cayley's invention to push their bikes to the limits. The light but strong wheel is a simple but blindingly clever invention. And there's one way to show just how it works. So BMX rider Dennis Wingham is lending me his bike.
The most important part of this wheel is the one thing you can't see. It's not the rim, it's not the spokes themselves, it's actually the tension in the spokes. That's what's pulling the wheel together. So what I've done, obviously, is take that tension out of the spokes. So now the wheel isn't holding itself together the way it should, which means we can see how much difference and how important that tension is. Good luck. It may not work as well as it did, sorry. Yeah, I think that's kind of proved the point. Take the tension out of a tensioned wheel and it's got nothing to offer at all. It's no good to anyone. Well, especially not Dennis. I think he might be cross.
So tension is the crucial principle. Cayley successfully achieved the first manned glider flight in 1853. And the bicycle business has never looked back.
Tension spokes allowed the wheel to outperform anything you'd expect of any of the individual elements. They'd be too frail, too weak to do the job on their own. But working together like this, they're immensely strong. So for me, certainly, Cayley really is the man who reinvented the wheel. But what's this got to do with Wembley?
The Wembley Arch spans the entire width of the stadium. That's the length of 3 football pitches end to end. But that's not all. It has to hold up most of the 7,000 tons of roof. Engineers had to make sure the iconic arch would be strong enough to take the load.
Now imagine this arch as a giant wheel rim. And, yeah, you've guessed it, the wires coming out of it are giant spokes.
Like bike spokes on a wheel, tensioned cables are the key to making the arch work. And Alistair Lenchner was the engineer behind the design. We're being led right up onto the roof to see just how it works. Yep, onto a thin roof with nothing supporting it from below. Nothing at all.
How thick is this metal?
This is 1.2 millimeters thick, aluminium.
1.2 mil.
Yes.
Could you use anything thinner? The roof flexes.
So here we are. This is a cable which, when you stood outside the stadium, looks like a little thread.
That is massive, isn't it?
It's a big cable, but it's actually part of the structure which supports the whole roof.
Well, the whole structure, actually, when you're down there, it looks delicate and fine, but up here now, we can finally get close to it. What's it doing? What's happening?
Yeah. This arch, it's not there just for decoration, though we think it looks great. It's holding the roof up.
These cables pull the roof up towards the arch. But that's not all.
But then we've got to make it stable, and these same cables hold the arch in its shape to stop it from buckling like that or like that.
So those cables really are working like the spokes on a wheel then, holding the thing in shape.
The arch and the cables work as a mutually supporting system. One without the other wouldn't work. It's the weight of the roof itself that tensions the cables and makes the arch stronger. 6 kilometers of these cables stop this enormous arch from failing catastrophically. And they mean that this 11-acre roof doesn't need any supporting columns.
Unobstructed